A few years ago, I was in a number theory course, hearing of Euler's function, struggling to understand what it was saying, what the function meant. Admittedly, in the background of this, I was continually distracted thanks to a professor from the year prior planting a seed of a simple to state idea, yet impossible to solve. No one knows. It becomes chaos. I was hooked. Surely this can be known. Surely I will solve this impossible problem. The professor begins with primes. Euclid taught us infinite amount of them. There are Mersenne primes. Fermat found some cool prime things. Here's a type of prime. Twin prime. Primes with a difference of 2. Are there infinite twin primes? No one knows, professor says, and something akin to, if you solve this, you can retire. Hearing this solidified an internal feeling. From then on, this was my problem. There was no way I was not solving it. A few years later, I've yet to solve it. I still don't know. Yet, I found some interesting things, most not so interesting. What follows is one of these interesting things. As we continue, keep these twin primes in mind. Again, we've known since Euclid there are an infinite amount of primes. Each of these primes differ by the previous prime and the next prime by some amount. It wasn't until 2013 when a bound representing that difference was finally known to recur infinitely often. 70 million! It has since been lowered significantly, but the question remains, infinite twin primes? This might just be the holy grail of unsolved prime number problems. It's clear that we start off with a frequent amount of twin primes, and they are certainly of significance in determining later primes. Yet, as we traverse down a number line, the twins, and primes in general, begin to spread out further and further and further away from each other. We simply don't yet know if there are an infinite amount of twin primes, and we have yet to find any relationship that isolates just these primes from all the rest, until we create a way to find one, until we discover one. Enter Euler's phi function. Euler's phi function is a way of keeping count of how many numbers are relatively prime to any given number. Let's take a look at a few numbers to figure out what that means. Let's find phi of 5. We ask, how many numbers less than 5 share any common factors with 5? Well, we know 5 is prime, so we know that no numbers less than 5 share any factors with 5. Then we would say that all the numbers less than 5 are relatively prime to 5. Phi of 5 equals 4. What about a non-prime? Start at 15, head back to 1, and count any stops made along the way. Stop at 12 because 3 divides 12 and 15. 10 because 5 divides them both. Each of these stops is a multiple of 5 or 3, and so it's not included in our count. Then the remaining numbers are relatively prime to 15. Phi of 15 equals 8. What if I take 2 primes, find phi for each, and multiply them together? Well, I assume it works as normal, so 6 times 4 is 24. Ask, does this make sense? The product is 35, and we know if we were to count all the numbers less than 35, leaving out the multiples of 5 and multiples of 7, since each of those numbers share a common factor with 35, that is, 5 and 7 are common divisors of 35, and they each divide their own multiples up to 35. So we add their multiples, 5 copies of 7 and 7 copies of 5. That gives us 12. But we counted them both twice at 35, so minus 1. 12 minus 1 equals 11. And this makes sense because we start with 35, and we have 11 numbers that are not relatively prime to 35, which leaves us with 24 relatively prime numbers to 35. Since we're still seeking to make sense of this function, let's continue to explore assuming this relationship holds for all primes and see what kind of results we might expect. Here, we might notice something. Let's flip our perspective. Instead of focusing our attention on the amount of relatively prime numbers to the product of our primes, let's look at the amount of non-relatively prime numbers to that product of our primes. In doing so, we can rearrange our equations like so. It seems we found a general form of an equation to phi of two primes, and notice that these two equations are equivalent. Clearly, we're playing with a more explicit way of describing this relationship, however, a less clean way of expressing the equation of phi. But it reveals an opposite view and helps give intuition to the function, and any intuition that can be found when learning math is always of significant value to the learner. Plus, maybe, just maybe, we've had some fun along the way getting to this point. But what if we have a high capacity for play? We need to keep going. Maybe I can rearrange like so and hope to squeeze something out of phi. Just as we re-express the term that corresponds to the amount of non-relatively prime integers, can we re-express the product of our primes? Any ideas? A good idea is to return to the beginning, ab ovo. Remember, the background of my mind was dominated by twin primes up to this point, so let's dig up what we know about twin primes and bring it to the front where our newfound intuition resides. Do we notice anything? Remember how I introduced twin primes to you? We clearly see there is a difference of 2, but do we notice anything else with any of these pairs? Maybe we can use the same idea of common factors that led us to the idea of relatively prime integers. Anything that these pairs share in common? What do we see sandwiched in between each twin prime pair we've seen so far? Again, back to the beginning. What's the first number in between? The second? The third? Ah, we see something. Each of these numbers are a multiple of 6. Okay, let's assume this is always true. It is. And continue playing with Euler's phi equation. Returning to the product of 2 primes, of twin primes, and combined with the idea they are always separated from a multiple of 6, can we re-express this product, keeping these terms in the output of their product, but with respect to 6? Well, what is the product? 35. 5 and 7, 6 in between. Where does 6 go? Ah, 6 squared is 36. 1 more than 35. Is this always true? Again, we assume this holds in our haste of play and seek to find a way to re-express the product with respect to the multiple of 6, and in this case, through the multiple of 6. Let's do it. And we've gotten back to 35. We can do the same movement with 11 and 13, back to 143. Okay, let's formulate this and substitute into our equation, and actually, let's prove this. Good math requires proof, So let's verify this is a valid swap and always true, since we've not seen it before with respect to this equation, and it'd be nice to know that what we find in our creative play from this point on is always true. We claim that these expressions are always equal, and to do so, we need to prove that we can get from one side of the equation to the other side of the equation, and we need to prove that we can make it back. The fraction on the right-hand side equals something. Let's call it x. If our equation is true, then this factorization must equal the product mn. So let's sub these values into the right-hand side and seek to derive the left-hand side. One direction down, one to go. Now we sub these values into the left-hand side and seek to derive the right-hand side. We've proved this expression is equivalent to the product mn. But notice something. The equations in the middle are true for all primes that we choose for mn. But once we do this, we've filtered our solution set, and this equation is no longer true for all primes. Unsurprisingly, our explorations have expanded our expression into an even more exaggerated state. Let's bring this back into focus and see what our new perspective offers.